This is section 14.9. And in 14.9, we're going to talk about using mass spectrum or analyzing a mass spectrum using the parent ion, the M plus peak. Now, in your book, they talk about first the methyl or the methane or analysis of methane using mass spectrometry. And here is a good example of the parent ion that we talked about in the last section. Methane has a molecular weight of 16. Its molecular ion, 16 here, is also called the base peak because it's the tallest peak. In every spectra, you should be able to find a base peak and label its molecular weight. In the figures in your book, in general, the scales are M over Z 5 between every major tick mark, and there are integer values. So it would be 16, 17, 18, 19, and 20. So sometimes they can get a little hard to read, but hopefully you can stick with me here. All right, so in analyzing the M plus peak, the book wants us to be able to understand how to find it every time. So they show us benzene first. And in benzene, what is clear is that the base peak is also the molecular ion, 78. It should be true in a lot of cases that in each little group of fragments, there should be a largest peak. And the molecular ion should be the largest peak in its little group furthest to the right, to the highest M over Z. So what does this mean exactly? So if we now switch screens to be the mass spectrum of cyclohexane, mass spectrum of cyclohexane, its molecular weight, C6H12, is 84, 72 molecular or mass units for the carbons, 12 for the hydrogens, to give us 84. The mass of the molecular ion is also 84. It's pointed out for us here on the SDBS, but you can see here in this little group, the 84 peak is the tallest. It happens to be the tallest. And I think in most cases that should be true. One thing to notice is that the base peak is here at 56, and that there is even spacing between the tallest peak in each of these groups. It's something to think about for a little later. But for now, notice that we found the molecular ion peak here. So we know the molecular weight of the molecular ion. One interesting thing is that if you start to add amine functional groups, NH2 functional groups, onto these molecules, they are important in mass spectrometry because they make the molecular weight now odd. So this is cyclohexylamine. So we replaced one CH bond with one CNH2 bond, where the carbon is bound to nitrogen and nitrogen bound to two hydrogens. So now there is an extra 16 molecular units, which 84 minus 1 is 83, plus the 16 from NH2 gives us 99. So if it's an alkane and there's an odd molecular weight, it's likely that there's an amine because the addition of NH2, 16, gives you an odd number often because you subtract one, or you subtract an even number from your original parent ion. Like in this case, 84 minus 1 plus 16. But if you have two nitrogens in the molecule, such as this cyclohexane diamine, meaning that there are two amine groups, now we subtracted two hydrogens and added two NH2 functional groups, to give us a total molecular weight of C6H14N2. From the 99 we had previously, we subtracted one hydrogen to give us 98 and added 16 molecular units to give us 114, another even number. And you can see here in the mass spectra of cyclohexane diamine that we found the base or the molecular ion peak at 114. Notice here that the base peak is at 56. And also, again, there is even spacing between each of these groups. So this was section 14.9.